My name is Tammy Miller. In this nucleophilic additions video, we're going to learn to draw the mechanism of carbonyl condensation reactions with ammonia derivatives. Before we draw the mechanism of a carbonyl condensation reaction with an ammonia derivative, we first have to get a couple of definitions out of the way. Carbonyl condensation involves the loss of the carbonyl oxygen. In other words, with my carbonyl carbon, I no longer am going to have this oxygen present on that carbon. And this happens because that oxygen is going to depart as a water molecule. So at some point we need to form that water molecule to have this occur. Once that carbonyl oxygen is gone, that bond needs to be replaced with something. And we're going to replace it with a carbon-nitrogen double bond. Another definition that we need to get out of the way is what an ammonia derivative is. An ammonia derivative is characterized by the number of hydrogens that are replaced by a substituent. So if the ammonia has one hydrogen that has been replaced with an alkyl group, in other words, a nitrogen, two hydrogens, and some sort of alkyl R group, this structure is called a primary amine. When it reacts with a carbonyl, then this will be called an imine. If, on the other hand, I have a secondary amine, this means that two of my hydrogens have been replaced with alkyl or R groups, just like this. This is a secondary amine. When it reacts with a carbonyl, this is now going to be called an N-amine. When we're looking at the mechanism of a carbonyl condensation with an ammonia derivative, there are some very key steps that we need to be thinking about as we go through the reaction. The amine, because that nitrogen has a lone pair of electrons, will always act as the nucleophile, and it will attack that partially positively charged carbonyl carbon. What this will do is shift the electrons from the pi bond in that carbonyl bond up to the oxygen. The hydrogen from the ammonia is going to protonate the electronegative oxygen. And this is because once the nitrogen attacks, the amine attacks, the ammonia derivative will have a positive charge. So it'll be a nitrogen with three groups attached and a positive charge. To make that happen, the electronegative oxygen is going to grab one of those hydrogens so that the nitrogen is no longer positive. The hydroxyl group will then get protonated, and this is important, by an acid catalyst. And remember, a catalyst means that it's going to help the reaction to proceed, but it is going to be reformed or rejuvenated by the end of the reaction. Once that hydroxyl has been protonated, it becomes water, and water is a stable leaving group and can leave. At this stage, the carbon-oxygen bond has to be replaced with the carbon-nitrogen bond. This is going to be a carbon-nitrogen double bond. The final step, because we had an acid catalyst, is we said that we have to have that regeneration of that acid catalyst through deprotonation of my final molecule that I have made. Let's actually draw a couple of mechanisms based upon these steps. For our first one, we're asked to draw the mechanism of a nucleophilic addition of a primary amine. When we look at our ammonia derivative, we see that it's got two hydrogens and one R group. This makes it a primary amine. First thing that's going to happen is our nitrogen is a good nucleophile because of that lone pair of electrons. And it's going to come in here and it's going to attack my carbonyl carbon. Now, the carbonyl carbon is going to force that pi bond up onto the oxygen. When this occurs, our oxygen is going to have three lone pairs of electrons, thereby making it a negatively charged oxygen. Our nitrogen has 4 bonds, which makes it positively charged. What's going to happen is our oxygen is going to, because it's negatively charged, come down here and grab one of these hydrogens so that it can leave the amine, and the nitrogen now is going to be charged as a neutral molecule. This is going to be the product of that. Now, both my oxygen and my nitrogen here are neutral. We said that the next step is going to be the protonation of the hydroxyl group with an acid catalyst. So here's my proton coming in with my acid catalyst. And what will happen is my oxygen on my hydroxyl group will come over here and will grab that. And that's going to give me water. My oxygen is positively charged, which oxygens don't like to be positively charged. So this is going to leave my molecule. And when it leaves the molecule as water, this is going to then be replaced by that carbon-nitrogen double bond. That carbon-nitrogen double bond is the double bond that is right here. This carbon-nitrogen double bond was formed when the electrons from our nitrogen came up and attacked the carbon right here. Once again, my nitrogen is positively charged, which is not its favorite. So what's going to happen is this hydrogen is going to leave the molecule, and I'm going to reform my acid catalyst. So notice the hydrogen's leaving. And this gives me an imine. Remember that when we do a primary amine as our nucleophile, we get an imine. Our next example, we're going to use a secondary amine. And I know that this is a secondary amine because it has 1 hydrogen and 2 R groups. The nitrogen on the amine, again, is going to be negatively charged. It's going to be a great nucleophile. So it's going to come in here and attack the carbonyl carbon on my diethyl ether, causing the pi bond to come up to my oxygen. This step looks exactly like the last one. Now I have a negatively charged oxygen and a positively charged nitrogen. The negatively charged oxygen is going to come down here and grab one of these hydrogens so that it can leave the nitrogen. Once that oxygen grabs that hydrogen, I'm going to end up with a neutral hydroxyl group and a neutral amine or ammonia derivative. The next step, just like on the last one, is going to be the acid catalyst coming in. And this acid catalyst is going to come in, and my hydroxyl group is going to grab that hydrogen. It's going to grab the hydrogen and make water. Again, oxygen doesn't like to be positively charged, so this is going to leave my molecule. When it leaves my molecule, this allows me to have the nitrogen-carbon double bond right here. This carbon-nitrogen double bond was formed when the electrons from our nitrogen came up and attacked the carbon right here. When we look at that positively charged nitrogen, we need to remove one of the bonds from it. And to do that, this hydrogen is going to leave, thereby reforming my acid catalyst. And I will be moving the double bond from the carbon-nitrogen to between these 2 carbons. This is going to be an N-amine as our final product. The mechanism for ammonia derivatives is going to be the same whether I have a primary or secondary amine. The difference is going to be, do I have an imine with a nitrogen-carbon double bond, or am I going to end up with an N-amine that has a carbon-carbon double bond? These distinctions will help these reactions to be easier for you.